Hello, everyone. My name is John Lehman, and this is a presentation for CSE 545 at the University of Louisville. My topic is going to be on knowledge distillation in machine learning models to create local AI, and we'll look at some applications in industrial and factory systems. What is knowledge distillation? Knowledge distillation is a machine learning training method where we use a larger model to teach a smaller model. And the goal of this is to make a smaller model that's faster, nearly as smart as the large model that's used to teach. If you think about it, it's kind of the way humans learn. If we had to gather all our information through firsthand experience, going out and collecting raw data on our own, we wouldn't be able to learn nearly as much as we can by taking in secondhand experiences and being taught by other people. The term knowledge distillation was first coined by Google engineers in a paper published in 2015. So, why should we use knowledge distillation? The short answer is compute cost. If you've been following AI over the past few years, you know that AI performance is pretty much tied to compute costs, and there's an all out arms race to get more GPUs, build more data centers, and basically scale models using just raw compute power. So, knowledge distillation allows smaller models to be operated without using so much compute. If we look at the chart here, we can see the compute costs over the last 10 years. Uh, about 10 years ago, the average cost to train a leading model was between $1,000 and $10,000. And looking up at today, most recently, this is published in 2024, but GPT-4 went for around 78 million in training costs, and Gemini 1.0 required about 190 million in training costs. So beyond just initial training, there's also a lot of reasons you might want to use knowledge distillation for your deployment needs. Any sort of offline, localized deployment where you have limited resources, knowledge distillation might be a good solution. Also, edge cases where large models aren't performing the best, you might be able to distill a model from a large model and then refine it that way. Let's look at kind of a history and some use cases for knowledge distillation. One of the first major milestones was DistillBERT. BERT stands for bidirectional encoder representations from transformers. It's a natural language processing NLP model. If you look at the chart on the right, you can see around 2019 when DistillBERT launched, these are parameters measured in millions. So models were really starting to ramp up the parameters and the compute costs. And right before DistillBERT, you had Megatron LM, which was NVIDIA's large model, which had 8.3 billion parameters. And then DistillBERT launched with just a meager 66 million. And as you can expect, the Megatron LM did perform better than DistillBERT, but it's not such a drastic performance that once you start equating for the compute cost, there's a lot of use cases for the smaller, more efficient model. And you can see this still today. It's a commonly used model. I just checked the downloads right before I started recording this, and it had been downloaded 13 million times last month. Stillbird's success didn't go unnoticed. A lot of the larger models started offering smaller, more compact models to go along with the big models. So Google Gemini now releases the Gemma models, which are trained using Gemini. Meta uses the Llama 4 Behemoth to train the Scout and Maverick models. OpenAI and Anthropic, they both offer API tools for developers to be able to train their own models. One kind of newsworthy controversy that happened recently was with the DeepSeek R1. You might have heard about it. They reported a LLM training cost of only about 6 million, which of course is a lot lower than those numbers we were looking at earlier. And this caused a big sell-off in the stock market and kind of a panic in a lot of the investing AI world. And the speculation was that DeepSeek used OpenAI's models to train its own models using distillation. It kind of brings us to our next topic, which is constraints of knowledge distillation. One of the main problems with distillation is the loss of accuracy. The student model can never really surpass the teacher model because it's always going to be dependent on it. So it makes it a poor choice for a leading edge model. Another issue is subliminal learning, that bad habits can be passed from the teacher model to the student model. If you've ever used ChatGPT, you might recognize certain speech patterns that it does over and over. If you then use those to train a student model, the student will also pick up those same bad habits. That could be a lot of different things. There's a paper by Anthropic where they were using a teacher model that was kind of obsessed with owls, and then it found that the student that was trained on that data also was obsessed with owls, which is pretty funny. Some other limitations of distillation are limited transferability. When you distill the model, it's going to lose its generality, which will make it less adept at doing any new tasks that it wasn't specifically trained on. And it's also very data sensitive. The data needs to be representative of what the teacher's data was. All right, let's start looking at some of the mathematical concepts behind knowledge distillation. In standard supervised learning, we train on hard labels. So, for example, looking at this image of a cat, we would say this is a cat with 100% certainty. In distillation, the teacher provides soft targets, which are probability distributions. So we might see something more similar to cat, 0.8, 80% chance it's a cat, 15% chance it's a dog, 5% chance it's a fox. And this structure is kind of revealing the semantic structure that the teacher learned instead of just the result. And by providing this to the student model, it can learn not just what's correct, but how those classes relate to each other, which can lead to better generalization on limited data. And this is especially important in real-world environments where labeling can be imperfect. Another concept we can get looking at these images is dark knowledge. So on the bar charts below, we can kind of see the difference between what a hard label distribution would look like and a soft label. And the dark knowledge is the difference. It's all that data that's lost when you're only evaluating a hard label. So in short, hard labels teach correctness, but soft targets can teach understanding. The next mathematical concept we're going to talk about is temperature. In a distillation model, logits are the raw score that are initially put out by the teacher model. Temperature is going to be a scaling factor that we apply to those raw scores. And we have the equation down there on the lower left-hand side. So you can see kind of the difference in the two bar graphs here. The left is a lower temperature and the right is a higher temperature. Temperature controls how soft or how informative the teacher's outputs are. As the teacher's output distribution spreads out, it shows how it views class similarities. So a lot of times in training a distillation model, you would increase the temperature to give it kind of more of that dark knowledge, distill more of the information out of the similar classes, not necessarily the right answer. But then when in practice, when you're deploying that model, you would use a lower temperature. So the model is going to be more decisive and given a clear answer. The next concept we'll talk about is Kullback-Leibler divergence, or KL divergence for short. Training a model using distillation, we will use this to compare the outputs from the teacher model to the student model and try to align those as close as possible. So the KL divergence quantifies how differently two probability distributions are. In our case, how far the student's predictions stray from the teacher's predictions. The teacher thinks the image is 70% likely to be a cat, but the student says that it's 95% likely to be a cat. Then we would penalize that model based on that KL term for the overconfidence. And by doing this, we are minimizing KL divergence, and the student will better learn to approximate the teacher's behavior. And this is what allows a smaller local model to mirror the reasoning of a larger cloud model. It keeps inference local while maintaining the accuracy. All right, we've covered knowledge distillation at a pretty high level. So now I want to start talking about applications. So my background is my undergraduate degree is mechanical engineering, and I've worked in factories for about 10 years now. So I have a lot of interest in industrial automation and applying AI within production environments and how exactly that will function in the future. So I want to look at some industrial AI context and some of the constraints of those environments. So there are hardware constraints. A lot of times you have limited access to compute power. Most industrial equipment currently runs on PLCs. There are going to be power limits, thermal limits for embedded systems that are on the floor. Operational requirements. Oftentimes, machines need to be able to make real-time decisions. This is going to require real low latency that you can't necessarily get with cloud-based applications. On-premises data privacy, protected any proprietary information. Machines have to be reliable. They'll have to work under any sort of factory condition. A lot of times this can be a lot of noise, it can be potentially dirty, dusty environments, non-stationary, things get moved around. So those are some of the constraints of working in an industrial environment. Now we'll look at which tasks within an industrial setting could be ideal for applying knowledge distillation, artificial intelligence. So there are currently already automated tasks within industrial settings, and there's also quite a few semi-automated tasks. So that would be probably the area that would best fit these applications. Any task that requires a semi-autonomous machine, but then needs a human input or perception in order to complete the task. So let's look at a few examples of what that could be. Things like vision and inspection, checking finished product for any defects, sorting different classifications of products that might come off the same line, sort of thing. Areas like robotics, which need guidance, also can do things such as like variable pathing, different inspections for moving environments. versus the current iteration of guidance systems. Another area that could be improved is machine monitoring and maintenance. Things like vibration, sound, temperature can all be measured with sensors. And so there are a lot of tasks that can require human monitoring for safety reasons, which could eventually be replaced by AI, which will be even safer without any distractions and can respond to these things much quicker uh, and with lower error levels than a human operator even could. Another area is industrial NLPs, things like understanding work orders to dynamically process orders or finish orders, understanding SOPs, sort of floor guidance and what needs to be done next, that sort of thing. So those are some areas where we could apply knowledge distillation. This was a case study that was published earlier this year. In this case study, a manufacturing team applied a semi-supervised KD framework directly into a cold-rolled steel production environment. The large teacher model was used to capture complex defect inspection patterns under realistic production conditions. Through distillation, the student model became small enough for edge deployment, yet retained high accuracy. So this is significant because in harsh settings with vibrations, variable lighting, heavy machinery, managing inference on site is critical for uptime and latency. This deployment showcases that KD isn't just research lab theory, it can be used in a real-time environment. This next study targets robot vision and its guidance under operational factory conditions, not just lab benchmarks. So in this example, a strong teacher was trained on limited labels plus a lot of unlabeled production imagery, and they were able to distill a smaller student model. And this model delivered 2 wins on the floor. The first thing was its robustness to different domain shifts. So you can think of like being able to handle different SKUs or variable lighting in an environment. And secondly, it was edge ready. So that means it was running locally with predictable latency. The authors report better generalization and throughput versus standard baselines and with less label requiring. So this is just another great example of AI on the factory floor. Okay, so let's talk about key takeaways. Knowledge distillation enables smart, efficient, and local AI. This comes with a trade-off. Usually the distilled model is going to be less accurate than a larger model, but the trade-off also means less compute resources and less operational costs. These KD models are trained with soft targets and then they're tuned using temperature and KL divergence. And these KD models are going to be well suited for Industry 4.0 requirements. So this real-time AI can improve safety, inspection, and maintenance. And the constraints of working in an industrial environment align well with the value proposition of distilled models. We went over a few real case examples, deployments showing that this technology is moving that direction, that KD models are being used in factories currently, and they're fast, safe, and factory grade reliable. And finally, we have the references for this presentation. So if there was anything in here that interests you, you want to learn more about distillation or look deeply into some of those case studies, I've got all the links and references there for you to look up.